So section A students, please acknowledge. Can you see the PowerPoint?
Yes, sir.
Yes, sir.
Okay, thank you very much. And section B students, can you see the PowerPoint, the first slide?
Yes, sir.
Okay, thank you very much. So let us begin today's discussion. So today's lecture is lecture number 27. So in this lecture, we will be discussing some of the numerical examples on LBC, that is linear block codes. We have seen in the previous lecture what is LBC. So basically, in case of LBC, that is linear block code, it's a combination of linear codes as well as block codes. It exhibits the linear property as well as the property of the block codes. Then we saw how transmitter and receiver will encode the data as well as decode the data. So basically, if you have a stream of bits, it is converted into blocks, smaller sized streams, and then the encoder will encode it with the help of some generator matrix. It will encode it and send to the receiver. When it is being sent to the receiver, it is sent through the channel. As a result, there is a great chance that the channel may corrupt the data. In that scenario, we assume that the channel adds some noise. So if the channel adds some noise, that ultimately reaches the receiver or the decoder, decoder will try to decode it. In order to decode it, it has to do some computations based on the received data. It has to compute something called a syndrome vector. And with the help of syndrome vector, it can decide whether the received data or received code word is exactly what was transmitted or not. So basically, with the help of syndrome vector, which is calculated at the receiver or the decoder will decide whether the data was error-free or there was error. So error detection is done. And later, this syndrome vector also helps in deciding where was the error, if there was error. Okay, so even the error detection as well as correction, both are possible with the help of linear block codes. That's what the theory we saw, how to calculate the syndrome vector or how to encode the data, how to generate the code word and so on at the receiver as well as transmitter. So we will see today an example here. So that gives us a better understanding of all these concepts, the theoretical concepts. So let us begin with that example here. So the example says here, let us consider a 3,6 linear block code generated by the generator matrix. The generator matrix is given below here. Also, let the data sequence, the transmitter wish to transmit, be this one. So the story here is the transmitter has a data that is 001. It wants to send the data to the receiver. Here, some more parameters are given. That is a 3,6 linear block code. So 3,6, this is of the format k, n. K is a number of input bits, that is 3. So that is what the question says us. It's a 3-bit input. The input bits are 0, 0, and 1. And this number 6 here, it is the total size of the block, that is n. N is equal to 6 in this case. So that means the encoder has to convert this data, which is 3 bits, into 6 bits, a code word. The code word size is 6. So these 3 bits has to be converted into 6 bits. So how to do that conversion? To do that conversion, it takes the help of a generator matrix. The transmitter and receiver agrees for a generator matrix initially. So that generator matrix's structure is given here. So basically, generator matrix is a combination of two sub-matrices. That is, one is the identity matrix, other one is the parity matrix. So identity matrix, you know, here. So the first part. The parity matrix is here. Altogether, this is a generator matrix. This is given in the question. Sometimes only the parity matrix might have been given. In that case, you need to find out the generator matrix. So again, since you know the structure of the generator matrix is basically a combination of identity matrix and parity matrix. So even if just the parity matrix is given, parity matrix means this part of the matrix. If it is given, you need to find out G. That means you need to append this identity matrix. So identity matrix will consist of only the diagonal elements having a number 1 unity. So that you need to add and generate the generator matrix. But in this question, the G is directly given, so you can uh, directly use this. In some questions, it is possible that the question will indicate only P. In that case, you need to find out G using this idea or this equation, what you call the relation. Okay. From this question, what else we can determine? One information which we can gather is the size of data. Data is 3 bits and the data pattern is also given here. Sometimes the data may be not given. In that case, you need to think what should be the data, because you know that the data is 3 bits. 3 bits data, what are the different combinations? We can have 0 0 0 0 0 1 0 1 0 and so on up to 1 1 1. So these are the different combinations, right? With the 3 bits we can have. So that you need to test for all those data bits. But in this case, the question is very simple or straightforward, that the data is specifically given as 0 0 1. Okay. Okay, and then other information is 6 here. So 6 indicates the size of the code word. So that means we need to add 3 redundant bits to generate a code word. So code word will have C1, C2, C3, C4, C5 and C6. Anyway, the first 3 bits are available here from the data itself. The remaining bits we need to add. So there is an equation to generate the code word, right? Do you remember what's the equation to find out the code word? C is equal to data multiplied by something, right? Okay. So with the help of that, we can find out the encoded sequence. That is what is done at the transmitter or at the encoder. And remaining all operations are done at the receiver. That we will see how to do this. So all those parameters we need to decide. I mean, we need to determine in this question. So I gave enough explanation about this question or the different possibilities with this question, because in some questions, I mean some exam papers, they just mention P. In that case, you need to find out G using this equation. In some questions, they only mention this number K comma N. In that case, you need to identify what is the data if data is not given. Because when the data bits are only 3, then you need to think about all the combinations that you can have out of 3 bits and assume that that is the data and do your computation. Okay, let us go to the solution now. First, from the given data, can we find out the code word at the encoder? C is equal to D into G, or D multiply G. Data we know. G is, fortunately, it is given in the question. So C consists of how many elements? C will consist of 6 elements because it's a 3,6 encoding system. 3 bits of data, and it has to be converted into 6 encoded bits. If you want more clarity, we are talking about an encoder right now. Then we'll talk about the decoder. So this encoder here, so this is the encoder, ENCI, right? This encoder has a data input that is 001. So this is the data input, D. This, based on this data, it has to encode it into a code word. So that code word we can get by using the equation C is equal to D into G. D is the data anyway, the input, and G is a matrix that the transmitter, that is encoder, and the decoder will agree. Initially, they agree on this particular pattern, and the communication will take place. So C is equal to D into G. So in this case, we know the G value, and you can easily compute what are the elements of the code word or how the encoded sequence will appear like. That is C. C is equal to D multiplied by G. So it's a simple matrix multiplication. I hope you know how to multiply row and column and row and column. But here addition refers to the XOR operation. So C1 is what? C1 we have to find out C1, C2 up to C6. C1 is this row multiplied by this column. So that is 0 and 1, multiply 0 and 0, and 0 and 1. So it's 0. Similarly, C2 is this and the second column here. So again, that will be 0 because you have 0 here and 0 here and 1 and 0 here. So that is 0. I guess the C3 will be 1 because you are multiplying this with the third column here. Even though the first two entries are 0, the third entry is here 1 and 1 here. So 1 multiply 1 is 1. Similarly, you can find out C4 or C5 or C6, right? C6 is this row multiplied by the last column here. So there is a 1 here, there is a 1 here. So when you multiply, you should be getting 1. So this is how we find out the different values of the, different bits of the coded sequence. So C6, total length is C6 or 1 to 6. So altogether we write C. What is this C? C is the output here, the encoded sequence. You gave this data that is converted into some coded sequence. What's the value there? That is 0, 0, 1, 0, 1, 1. That is C1, C2, C3, C4, 5, 6, C4, C5, 6. So you notice here the first bits are almost the data itself, 0, 0, 1. And remaining bits are the check bits that are added to make this data in an encoded sequence, so that even if there is noise added in the channel at the receiver side, at the decoder side, by reading this, the decoder can understand where was the error, or how to correct that error, and so on. So this is the whole operation that takes place at the encoder. So basically now we gave the data input to the encoder. Encoder encoded it using some mathematic here, that is C is equal to D multiply G, and encoded it. It's like we are protecting the data with the help of a password, right? Yes, now the data has changed to some other sequence, a coded sequence here, a crypted sequence here. All right, now we will see what happens at the receiver. The receiver has to do some mathematics again here to understand from this code word that whether there was any error or not. Okay, to check that, to make it more, not very simple, to make it more complicated or more realistic, we will add noise also to this. So here, if some error introduced by the channel, so encoded sequence C we have obtained, that is what the encoder has transmitted. This transmitted data has to flow through the channel. In the channel, we assume that there is some noise added. There is possible that noise is added or not. But let us take it more realistic. Assume that there is noise added. If noise added, how to recover? If no noise is added, it is very straightforward at the receiver, that the first k bits are the coded sequence, the data bits. Because C in the previous slide we saw, it had 6 bits, right? The first bits were data itself, first 3 bits, and remaining bits were the check bits added. So if there is no noise added, then receiver's job is very simple. But it is not the case most of the times, because channel will introduce some noise. So we will think that channel will introduce noise, and then we check whether the receiver can understand that there was noise added and can it correct that error. All those things, all those steps we will see. Okay, let us think that the channel has added some noise or error. Error is indicated by this vector. 0 means no noise added. 1 means there was some noise added at some point. Okay, so at this point, second bit position, some noise added. So, okay, noise is added. Now that data comes to the receiver. That's at the decoder. What is that? The data that comes to the receiver or decoder, that's equal to code word and also the noise, right? If you want, I will write it as in the form of a diagram here. So initially we had some data here. Data was the input here, right? This data was converted by the encoder as a code word. Okay, encoder, en, encoder, and it was converted as C, right? This is a code word. Now it comes through the channel. This is a channel, and in the channel we again added some noise. I mean, channel added the noise by itself. That the noise is E. Now we have the receiver here or the decoder here. I write DC decoder, decoder here, and what is received at the input here? R. We write it as R. R is a combination of the coded sequence that is here, coded sequence C, as well as the noise that is added here. That is what is written here. R is equal to C, and here R is equal to C added with the noise. That is here. The input here is R. It's a combination of the code word and the error sequence. Now, based on this value of R, now decoder has to think what was the error. Was there any error? If there was error, how to correct it? That's the job here. In order to do that, it has to do some mathematical computations. That is, it has to find out some syndrome vector, okay, and also some parity matrix it has to consider. Okay, so this is the coded sequence C. This is what we have found in the very first step, C. And this is the error. We thought the channel has introduced this error here, right? So altogether, what do we get? R value. R value is the this operation on these two bits. 0, 0 is 0, 0, 1 is 1, and so on. This is a bitwise XOR operation. Okay. So R is this value. Notice here, the R that we received here is this 0, 1, 1, 0, 1, 1. Actually, what was the code word transmitted? Here, code word. That is 0, 0, 1, 0, 1, 1, right? If there was no error, if the error was 0, then we would have got R is equal to C. But there was some error we assumed the channel has added, right? Error. As a result, R is equal to C plus E. C plus E. As a result, the error value is this much. It is not same as the code word, right? That means there is some error. So where is the error? You can see when you compare these two, you'll come to know the error is here. The second bit has got affected by the error. Second bit of the code word has got affected by the error. We intentionally added in this case, but channel may add it anywhere, this error. So this indicates that there is some error because R and C are not the same. From this equation, we can easily conclude that if the error value is 0, then R is equal to C. Here R is not equal to C. That means there was some error. So error is in the second position. By comparing this, you can conclude. Okay. Now, how to address this error? So in order to do that, at the receiver, it has to find out the parity check matrix H. How to find out H? H is a combination of the parity matrix P and the identity matrix, right? The orders are mentioned here. Identity matrix will have an order of n minus k. N is 6, k is 3. So I3. And the PT, it's a transpose, transpose of a matrix. So P, do you know what's the value of P? P was given in the question, if you remember. G was given in the question. G is what? G is equal to I and P, right? So from that, you can get the value of P matrix. You just need to convert find out the transpose of that matrix. So P is given in the question. You find out P transpose, very simple. And I, you can write it by yourself, which is basically an identity matrix. That means you have only diagonal elements of this order, where all the diagonal elements are identity or 1. So you combine those two matrices, I mean, right side by side, or extend this matrix. So that gives us the parity check matrix. So the receiver has to find out H. How receiver will find out H? Because it knows the value of P. The transmitter and receiver has a pre-knowledge of P. So using P, it can find out P transpose and identity matrix. Yes, it knows. It can find by itself identity matrix. So altogether, that is H. That is the parity check matrix. H is this is P transpose, and this is the identity matrix of order n minus k. Okay. Now, is it done? We have to find H transpose, right? The transpose of the parity. H is already found. You just find the transpose of that. That means you convert the rows into a column, second one, and third one, and so on. So H transpose basically is of this pattern. In case of H transpose, the first elements are P and remaining elements are identity matrix. If you want, I can show you here. The first elements here are P and the remaining elements here are the identity matrix. It has two parts because we computed H transpose by considering H. H consists of I and P, right? So when we make it as H transpose, the P and I, it is, I mean, even that are getting exchanged. So H transpose is here, P and I. So with the help, why do we need to find out H transpose? Because the receiver has to find out the syndrome vector. Syndrome vector is what? R multiplied by H transpose. That's why we found H transpose here. R is already determined in the previous step, right? R is a combination of the code word and error. R is equal to C plus E, right? So that R you need to multiply with H transpose. That gives the syndrome vector. With the help of syndrome vector, the receiver or the decoder will decide whether there was error or no error. Ideally, the syndrome vector should be 0 to indicate that there is no error. Uh, but if the syndrome vector is not 0, then it indicates that there is some error. And it can also decide where the error was. That is error detection, not only error detection, error correction also. If you know where the error is, then you can take suitable action. I mean, you can just need to flip. If the second position has an error, that means you need to change the second bit. What is the second bit? Changing the second bit means if it is 1, make it 0. If it is 0, make it 1. Because only two possibilities we have. We are dealing with binary data. Okay, now receiver has to find out yes, the syndrome vector. So S is what? This is R. R is a combination of, I mean, C plus E is equal to R, right? This we have already found. R multiplied by H transpose. H transpose also we have found in the previous slide, H transpose. So this is simple math, R and H multiplication. So this vector multiplied by this column will give you one value. So addition, when you do the addition, it's a XOR operation. So 0 and 1 is 0, is 1, 0, 0, and again two zeros, right? So basically, I guess only this 0. Here we have a 1 and remaining all are zeros. So 1 XOR with zeros it should give you 1, right? Yeah, the first item is here. Similarly, you multiply this and this column and keep XORing each of these intermediate products and you should be getting 1. Similarly, this row and this column will give you 1. So that's all about syndrome vector. So what's the conclusion here? Syndrome vector, what has happened to the syndrome vector? Is it 0? Because we know in the theory, if you go back to the previous lecture, lecture number 26, we discussed that if syndrome vector is 0, then no error. Otherwise, you need to think. I mean, the receiver has to think. Okay? So here, the error correction stage. The matrix X is non-zero. It is not 0, right? There are some ones here. That means there is error. So error is detected. You see here, yes is same as the second row of H transpose. H transpose, the second row, is all ones. If you wish, I can go back to show you. There is H transpose. Here, H transpose. All rows are 1. That is same as yes now. So there is some hint here. Okay. So you please remember, in general, if S is the same as any ith row of H transpose, then there is some hint between the ith row number I and S. In this case, the S is same as which? Second row. So there is some relation between this. To understand the error. Okay, so here, S is the same as the second row of H transpose. The receiver understands that the second bit is in error. Okay, since it is similar to the second row, that means second bit, this particular ith bit in general, ith bit is in error of the code word. Okay, so error is detected. We have found where is the error. Error is the second bit, because the S, contents of S, is same as the second row. In general, if the contents of S is the same as the ith row number I, then that particular ith bit has an error. Okay, next. Error is detected. Now the error has to be corrected. It's very simple. The decoder changes the status of the second bit in R by adding E to R. Adding means mod 2 operation. So what is that? This is R and this is E. What do we get? Can you compute? R and E. When we do the XOR operation, we should be getting something like this, because 1 and 1 are 0, right? Actually, we added the error here. During the reception at the decoder has noticed that S is the same as the second row of the H transpose. That is a transpose of the parity check matrix. So second item or second bit has error. That is what detected at the receiver by seeing the syndrome values and comparing with the H transpose. So how to correct it? You just use that error pattern itself and XOR with the received bit. That should give us some sequence. Is this sequence same as a C? It should be, because we are doing the reverse math, right? So that is same as a C. That means we have corrected the error, because we wanted C without any error, but intentionally we added some error. Otherwise, we were expecting just the C. Okay, so error was detected at the second position, and the receiver did some math here, that is adding R and E, and it got the code word. So it was able to recover the code word, right? So once the code word is known, then the data is very straightforward. The first k bits are the data. Okay, so in this case, an important observation let us make: single error in the received vector can be corrected. Of course, these elements, rows should be distinct, because if two rows are same, that means maybe second and fourth rows are same. That means second bit is a problem, fourth bit is also a problem. That is not possible. Only single error, single bit error. Error in this case, error was added in one position, right? If there are two positions, you add the error, then this receiver will not be able to identify such errors successfully. So the main limitation here is it can detect the single errors. and also correct it. Single bit errors can be detected and corrected. It's possible that sometimes in a communication system, we have burst errors. That means you transmit some data. For example, you transmit this code word, not just one place. At many places, there are errors introduced. Maybe a sequence of bits continuously, second, third, and fourth bits are corrupted. Then this coding scheme will not work. We need to have some other coding scheme. Okay, there is a combination of that is called as convolution code, but not exactly convolution code. It's a combination of convolution codes. Coders will help us in detecting burst errors or solving the burst errors, not linear block codes directly. Okay, this is regarding how when we know some data to be transmitted, we can encode that data at the transmitter, and how the receiver can decode that data by detecting as well as correcting the errors. That's what the whole story about this example. And this gives a mapping between the theory and the actual scenario where we transmit data using linear block codes. Yes, please ask any questions if you have. Okay, if there are no questions, I move on to the next part. Because in this theory, not only this example, in general, we have some special properties we observe. One proof I had left in the previous discussion, that is C multiplied by H transpose becomes 0. How? I said I will solve it in the next lectures. Maybe I think I have that now. So this is one special property of linear block codes. Every code word C of a linear block code must satisfy this condition. How to prove? C into H transpose. C is the code word. It comes to the receiver and receiver computes H transpose. You multiply these two matrices or vectors, you get a 0. How? Very simple actually. If you see the structure of H transpose, you will understand. Okay, we know something here. G, generator matrix. What is G? G is a combination or extended matrix that is formed due to the combination of the identity matrix and the parity matrix, right? G is equal to IP. G is equal to IP, okay? So this part is the identity matrix and this is the parity matrix. Parity matrix, generally, they are generated by using some polynomial equations, and that is shared between the transmitter and receiver. For example, if any communication system that uses linear block codes, then they will stick on or they will pre-decide what kind of parity check matrix I need to use or we need to use. They will use the same thing. For example, in case of Wi-Fi, this is another example, not directly related to LBC, linear block codes. Some other example. For example, in case of Wi-Fi, we have a communication system, right? You have a Wi-Fi access point or you have a mobile phone. You send some data or receive some data between the mobile phone and the access point at home, maybe a router, or in the opposite direction, access point sending some information to your phone and so on. Anyway, in general, Wi-Fi, if you talk, or a Ethernet system, you have a wired internet connection from between your computer and the modem. Again, we have some communication there, right? Maybe you are sending data or receiving data and so on. So they will decide their parity matrix based on an equation of a polynomial equation. It may be 32 bits or 16 bits. So there will be an equation, polynomial equation, like x power 15 plus x power 13 plus x power 7 and so on. So accordingly, the parity bits will be decided. That means they will one standard for maybe Wi-Fi or Ethernet. They will stick on to one particular equation to say, or a bit pattern, or in to be specific parity matrix, and they will communicate in that way. Okay, similarly here, the transmitter and receiver knows that parity matrix. Okay, so with that help of that, they can find out G. With the help of, that means the transmitter can find out G. Similarly, with the help of G or with the help of P, the receiver can find out H, H transpose, and then S, right? Okay. So H transpose is what? This happens at the receiver. To find out H transpose, you need to know the P. I said transmitter as well as the transmitter as well as receiver knows P. So with the help of P, it can find out H transpose also at the receiver. Okay, so the general equation here is C into H transpose is equal to D, G and H transpose. The data and G, D and G is what? C, right? C is equal to, the first example we found, the very first point, C. How to find out C? It's code word that is equal to data multiplied by G. Okay, this is basically C multiplied by H transpose. Left hand side and right hand side, same. Okay, now D. D is same as here. G is what? We are just expanding what was given here, or the basic definition of G is a combination of I and P. And what is H transpose? H transpose consists of the P matrix at the top part of the matrix, and then the remaining elements are the identity matrix. So we have D, G here, and H transpose here. Now we are just doing a simple math here. That's equal to, I mean, this term can be simplified as D multiplied by, you have a IK here, IK here. So IK multiply P XOR with P multiply In minus K. Then this is an identity matrix of order N minus K, and this is of order K. And these are the parity matrices, that is this or this. Then we go on to simplify it further. That is, okay, there is a common mathematical property here. The matrix is multiplied by an identity matrix. In the previous slide, you see P multiplied by I. So when you multiply P and I, the value of P does not change because you are multiplying by an identity matrix. So C into H transpose is equal to, basically, the right hand side becomes D multiplied by P XOR with P, because we will be multiplying P by identity matrix. Here also there was an identity matrix. So when you multiply identity matrix and any other matrix, there is no change in the value of P. So it is P itself. So P XOR P with the D from the previous step. So P XOR P is again simple math here. If you XOR the common elements, the value becomes 0. P XOR P is 0, right? So D multiplied by 0 should give us a 0. So this is the proof of how we can find out C into H transpose. Actually, I wanted to give you this as an assignment for you to discover, because when we discussed about the theory, if you have observed carefully in the previous lecture, this was clear. I mean, I went through these steps. That's why I left it as a discussion in the future. So right now I have solved it here. C into H transpose is equal to 0. So this is the proof of this relation. Why coordinate sequence multiplied by H transpose will be 0. Okay, now let us move on to another property here. If there are two code words, C1 and C2, in a linear block code, then the sum C1 plus C2 is also a code word. So this property comes from the very definition of linear block codes. That's a linear property, right? In case of linear property, we have witnessed that when we have two or more than two code words and we add them up, sum them up, then the resulting vector, that should be one of the elements in the code word set initially, right? That means that's also a code word. So linear block code consists of the term linear. I mean, linear block code also exhibits that linear property. We can claim this as a theorem. If C1, C2 are the two code words in a linear block code, then their sum, that is C1 plus C2, is also a code word. This is a theorem. So how to prove this theorem? Or it's a property. How to prove this property? Okay, every code word C of a linear block code must satisfy the condition C H transpose is equal to 0. In the previous property, we have witnessed this Y C H transpose is equal to 0. And this should be exhibited by every code word. Now, we will extend this relation to this theorem. That is, if instead of C, you have two code words, C1 and C2, then it also should follow this. C1 H transpose is equal to 0 or and C2 H transpose is equal to 0. Basically, we are generalizing the original theorem, theorem number 1, earlier we discussed. Now let us consider a simple math operation. What? C1 XOR C2 and H transpose, because they are both zeros, right? C1 H transpose is equal to C2 H transpose. From that, we collectively, we have this common term here, C1 H transpose and C2 H transpose. That's equal to C1 H transpose plus C2 H transpose. So this comes from here, or this comes from here. Okay. C1 into H transpose is a 0 here. This comes from this, the general property. Yeah, C2 into H transpose is also 0. Okay. So when we have zeros, what happens? 0 is a code word, right? Do you remember? We had solved one question. I think that's regarding linear codes, the property. If a code word C has multiple sub code words, C1, C2, and so on, to check that C is linear or not, what do? We add up every subcode. And if the newly generated subcode is an element of the original code, maybe I should write here to make you understand better. For example, C is a code word or a set of code words. It has some other code words, C1 maybe 000 or 000, okay, or C2 maybe something else, 101, okay, 101, something like this. So C basically here has two code words, C1 and C2. And C1 has a bit pattern, as mentioned here, 000. C2 has another bit pattern, 101. To prove that C is a linear code, then when you add up C1 and C2, what new sequence what we get, that should be either C1 or C2. Okay, addition of C1 and C2 should give us either this or this. Then C is the linear. So C1 plus C1, what do we get? Or C2 plus C2, what do we get? We get 0, right? XOR of A XOR A, that relation or that structure. So 0 here, this is 0 is also a code word. If you consider any code words, any linear codes, 0 is a member. Okay, so even if it was not 000, maybe it was 111. Even in that case, you XOR C1 plus C1, you get zeros, right? So 0 is a default member of the code words. So 0 is here. This proves that C1 and C2 are also code words of linear block code C. Okay, 0 is a default member of this code word. So that gives us directly that the idea that C1 and C2 are also members of this linear code C or vector C. So this is how we prove this particular theorem. Okay, so this is another property. Yes, shall we move on to the next example, or if you have any questions, I will be happy to take up that. Otherwise, we will move on to the other question. But, the time is 12:22. Okay, let us take up the questions because this will take maybe around 20 minutes more. Or I will explain the questions to you, this question to you, and you try to solve it by yourself. I can have a discussion, brief discussion in the next lecture. Okay, the question is here. Consider a linear block code with n is equal to 6 and k is equal to 3. So by reading this, what do we get? We have 3 data bits, and we want to convert these 3 data bits into a code word whose size should be 6, right? Okay. The check bits of the code words are derived using the relation here. What are check bits? Check bits are the redundant bits that we add, right? So basically, I will give you a few more details here. We have some data. Data D is, I don't know. Okay. This is K bits. This data is K bits, K bit data. We want to convert these K bits into a code word N. Its size is 6. So when you convert it into code words, you will have C1, C2, C2, and C3, C4 up to C6. Okay, so C6. So many bits you have in the code word. Basically, you need to transform these K bits into a code word of N bits. That means, okay, I'll write C3 also here. Since the data bits are 3, because K is 3 here, the first 3 bits in the code word will be data bits itself. The remaining bits, that is C4, C5, and C6, should be the parity bits. Sorry, they are the check bits. Check bits. Okay. So how to generate those check bits? C4, C5, C6. That is given here. You need to do some mathematical operation here. D1 is a data bit, first data bit, second data bit, and D3 is a third data bit, and so on. So using that, how can you generate C4, C5, C6? So here, okay. So C4 is the fourth code word, fifth code word, and sixth code word here, C6. So how to generate C4? C4 is nothing but D1 XOR D2. It says that there are 3 bits in the data sequence. D is equal to D1, D2, D3. And using that D1 and D2, we generate C4. Using D1, D2, D3, adding up them, you get C5. Adding the D2 and D3, you get C6. In this way, you can generate code word, I mean, the additional redundant bits of the code word. So your code word should look something like this. Your code word matrix C will be something like this. It's a vector that consists of data bits D1, D2, if you compare the previous example, there the data was given as something like 101 or something. Here nothing is given. So C4, C5, and C6. So this will be C4, and this is C5, and finally you have C6, and this is C5. Okay, this is C5. Okay, so you have to generate C4, 5, 6 here using D1, D2, D3. So do you know what is D1, D2, D3? You don't know, right? So you need to think when you have 3 bits, what different combinations you have. With the 3 bits, you can have 0, 0, 0, 0, 0, 1, right? You can have 0, 0, 0, next to 0, 0, 1, and so on up to 1, 1, 1, right? So this is your data set. You can have any of these combinations as the data bit. Then how do you generate C4, 5, 6? Based using this logic. Okay, you get C here. Then you find the generator matrix G. How to generate the generator matrix? G has a relation I and P, right? So do you know the parity matrix? Or is there any other way to find out the parity matrix? Okay, that's the next point you need to think. Next, find all the code words of a linear block code. How to find all the code words of a linear block code? To find all the linear block codes, you need to find all the combinations of the data. For example, you have 0, 0, 0, 0, 0, 1, 1, 1, 1. All that should give you all the combinations based on you can generate C4, 5, 6, C4, C5, C6 using this relation. And you should get all the linear block codes. Next, find the error detecting and error correcting capabilities of the code. So you need to consider some error pattern and just follow the steps that we discussed in example number 1, previous example. And then also find H and H transpose. You know the equation how to generate H. H consists of IP, right? And take the transpose of that. So these are the different ways, I mean, steps to solve all these questions. Okay, I think I will leave it at this point and I will go for your questions. Anyway, we will discuss this in detail in the next class. I have the solution right now, but maybe I will exceed the time. So, okay, students, please, from section A, if you have any questions, let us discuss that. Elvin, you have any question?
Sir, excuse me, sir.
Yes, please tell me.
Sir, why we call this codes are linear block codes? Sir, why we call it a linear, sir?
Okay, so linear block codes, we had has two items, right? One is linear, other one is block. This is what I discussed in 26, lecture 26, the beginning. Okay, I will just repeat. Linear, because we have a linear property. You add any two code words, you get a new code word. That's also a member of a code word family. Such as, oh, I had an example, exclusive example earlier, but okay. A large set, if you consider, of a code words, what you generate, it has many other bits, right? When you add those bits, you will get a new bit pattern. That new bit pattern also belongs to the original code sequence, what you consider. That's a linear property. Addition of two things giving you a new thing, that's also can be mapped to the original set. That is linear. Block code because it has a block of data we consider to do this operation. Encoding is done block by block. You have a large sequence of bits, maybe you have 100,000 bits. You don't take all those at a time, or bit by bit we don't do. We consider a block. If you have 100 bits, you take 10 bits at a time, do the operation. Next, go to the next 10 bits, do the operation. Block. So this linear block code combines both. One is a linear property, it exhibits. Secondly, it considers the data as block of bits. For example, k comma n. We consider 3 bits at a time, convert it into 6 bits or 7 bits. Next 3 bits, again convert it into encoding. So it combines both. I mean, it has both. So it's a linear block code. Or you had other kind of questions? I mean, because this is basically the definition. You wanted something else?
No, sir, I got it, sir.
Okay, thank you.
Thank you, sir.
Any other students having questions from section A? Okay, I will come back to section A, but I'll go to section B. Students having any question from the class representative?
I don't think so, sir.
Okay, so the students, section B, any student having any question? Yes, please ask.
No, sir.
Okay. Other students, I mean, any section A or section B, any student having any question, please ask me. Okay, anyway, if you have no questions, no problem. But please go through these slides. I have already shared these slides. I will also upload the video if you want to hear the explanation. And another thing is, okay, that's it. That's the end of today's lecture.